All right, everybody. I hope you had enough time to go through the quiz. And now let's begin today's lecture. I just typed it into the comment box or chat box. You can click that and view the direct link. Again, I'm going to now, like I did last time, mute myself in the Zoom, but I can hear your feedback. Enough time to go through the quiz. And now let's begin today's lecture. I just typed it into the comment box or chat box. You can click that and view the direct link. Again, I'm going to now... Okay, so what we're going to do today is we're going to continue and finish the last series about the phase behavior in polymer solutions. So in today's lecture, what we're going to do, in addition, what we discussed in the last two lectures, is talk about several unique conditions into the phase diagram. We're going to discuss what is the critical temperature, what is the critical concentration, and how do we construct two characteristic curves in the phase diagram. Those two characteristic curves are the spinodal and binodal curves. We actually already discussed quite a lot for the spinodal curve. The spinodal curve is basically discussed when your system will going from a stable to non-stable state. So this is where we said it's going to be two-phase if you are within the spinodal cone. And the definition is quite straightforward. We already talked about that quite a bit. Let me insert a couple empty slides, and I'll use this empty slide to do a short discussion. So what we discussed is already how we get delta G based on Flory-Hagen theory and based on phi 2, and we can get the energy diagram, which is what type of delta G you would expect. I'll give a random one, and we basically discussed if this curve concave up or concave down will direct the system if it was spontaneously phase separate or not. And we discussed if we take a second derivative of delta G with respect to phi or x, no matter what it is, they will give you the similar results. This will define what it is a phase behavior for a spinodal curve, okay? So we're going to use this then to construct what we call a phase diagram, which is the temperature versus the phi 2 curve. And you guys already see we can have two phase somewhere there and one phase up here. And the question today is going to be addressing how can we link these two and how can we understand, for example, critical temperature, etc. So coming back to the lecture note. So here, now this is where we're going to do, and how do we get there? And we talked about spinodal is already given by second derivative of your delta G. So this curve is quite straightforward, right? This dashed line as shown here. I hope you guys already know what this means, and you don't have any question related to this particular two-phase with respect to the metastable phase, this dashed line. So how about the binodal case? This is a little bit complicated. So let's go back to a discussion about what a binodal case is. This relates to what is, we call it a metastable state. If you have a system is potentially stable at that particular temperature, then it will be happy to stay there. So this is an example we can give to you guys to see here. If we have a two-phase example where you have something sit right in between this binodal curve, which is defined by tangent of your losses energy with respect to your delta G curve. This will define the 2 points of the binodal. Okay, so binodal point to left, we can call it, and you can have a binodal data point on the right, right? So those two data points together, they define where your binodal curve is. If we go here, so if we fix a given temperature for this phase diagram, this would define as a binodal point A and B, and these two are the spinodal data point. And I want to first focus on this to make sure everybody understands. So there is one more curve I would like to show everybody. So this would be the delta G with respect to the phi curve for a generic material. So what you are looking at, y-axis is delta Gm. That's a free energy. And x-axis is the phi, which is volume fraction for one of the components in your binary blends. And now we plotted the two kind of curve together. We have a dashed curve and a solid curve. Within the same solid curve, we plot 3. And the differences with respect to those 3 are just a different temperature. So if we increase or decrease the temperature, our delta G curve will be different. And you should know this because one of the parameter, delta entropy, is dependent on the temperature. So your delta G will be equals to delta H entropy minus delta Ts. So there's a temperature term there, and this will influence the shape of your delta G. And this is what you see in 3 curve. And we kind of discussed it as well in the last lecture. Depending on the magnitude of the entropy, you would have this local bumps comes into play, and these local bumps will result in unstable of your sample. If there's always going to be delta G concave down, then you're always going to mix, and this will be the one phase, very simple problem. So with respect to 3 different temperatures, now we have 3 different data points, and these 3 data points are going to be spinodal, binodal points. And every time we change the temperature, you would generate a new spinodal and binodal point. And this is why, now if we do it repetitively, you can plot a phase diagram, which is plot as temperature with respect to phi. Okay, so this is how we get. At each G curve, you would get a new binodal curve, and we can call it A prime, B prime, D prime, and E prime. So these are going to be a new binodal point at this particular temperature. We can just call it T1, T2, T3, 3 different temperatures. If you do hundreds of different temperatures, then you can obtain this very smooth line for the phase diagram. So on the phase diagram, we explain what is a binodal, and binodal is where you would get the tangent of this red curve with respect to your delta G curve. It's not the minimal point, so please be mindful for that because they are very different definition. Okay, so this will be this dashed line tangent with the delta G. And why we need to worry about tangent? In this case, this will make sure when you have phase separation, it can phase separate into these 2 phase cases, and their total system energy would have the maximum drop. Now, the second question we want to address today is there's a couple unique points. First one we want to talk about is what is TC, the critical temperature. The critical temperature defined as a temperature above which your material system will be always mixed. Okay, so in this scenario, no matter what composition you put in here, if we draw a line along horizontally, we can see it's always going to stay in the one phase case. So it's probably easy. We go back to the last curve. So this is a good phase diagram. So if our temperature is above Tc, then when you mix 2, no matter it's 1:3 ratio, 1:1 ratio, or 2:5 ratio, it's always going to sit in this one phase case. And when your temperature drops and when it intercepted with two phase, that's where we define as critical temperature. And we know below this temperature, you potentially can have some phase separation happening. Okay? So the phase diagram is basically can be obtained from the definition that you would have an overlap of the phase diagram from spinodal and binodal phase. And this is where these two phase diagrams actually intercept, or these two curves, okay? The spinodal and binodal just joins where it is critical temperature, Tc, okay? So there is a little bit mass equation that we need to do, and we can just apply this very simple knowledge, because at this critical point, as you can see, not only the first derivative, second derivative of delta G with phi will be 0, but also the third derivative, okay? So if we apply the mass, I wouldn't talk into too much and dwell too much on this mass, but simply speaking, we apply this Flory-Huggins equation. This is a delta G definition from the mixing of, in this case, we use a generic term where you have N1 defined as material 1 with dP of degree of polymerization equals to N1, and second is N2. And we can just apply a simple derivative equation and to get following relationship. And hold on there, we have another step we need to take where we need to have a second derivative of the first delta G, what we got from the last equation, will also need to be 0. So we need to apply another derivative with respect to the phi to this particular equation. And you would get the following equation, and this is where is set to 0 when you have critical temperature, okay? So in this case, now you would be able to get what is the chi parameter when it is at that particular critical temperature. So what this means is if you define this would be equal to 0, then you can rearrange this particular equation to reach what is a critical chi parameter. And this is used when you want to understand what is critical chi value you need to make sure your system is always miscible. So what that means is chi is below this chi s, your system is always going to be mixed, okay? And we also discussed briefly in the first lecture that chi effective is defined as a constant and as well as a dependence on a b. A and B here are constant, okay? These are just a parameter. And T is the temperature. So based on the symbol of where A and B are, you could get different values of and dependence of the chi with respect to temperature. Let's say if B is negative, then increasing of the temperature will increase the chi, okay? Because if you plot this, if this is negative, increase the temperature will reduce the negative magnitude of the B and thus increase the chi value. And there's also cases if B is positive, then it's a little bit hard to read. Chi increases with T, is what I wrote here. And if B is positive, then it's other way around. The temperature goes up, your chi drops. So if we know that if we get a value of this particular equation and we can back calculate what is Ts. T is a critical temperature, and there's nothing fancy. We just applied chi into this particular equation, and this is what you would get in the Ts. And Ts here is a definition of critical temperature. If we know what is the phi, what is N1, and you know the constant A and B, you can know what is the critical temperature your system will be behaved as a mixed or non-mixed phase. And as you can see, chi is very important. This chi value defines if your material will phase separate at high or low temperature. If you can measure the chi between a polymer and solvent, it's already a very good achievement, which allows you to know a lot of phase behavior for those two combinations. But to keep in mind that this is not a universal chi you can determine for a polymer. You always need to consider the pair between your polymer and solvent. So, for example, toluene and hexane. Maybe I use another example. Polystyrene and toluene usually has very low chi, but if you have toluene with acetone, for example, then your chi will increase quite a lot. So you cannot use the polystyrene as one example to talk about, and one component to talk about chi. It's always a pair, okay? The other critical parameter we can have is where it's going to be dependent on phi c. What is phi c? If we go back to the phase diagram, so when you have a Tc, which is critical temperature, and for this particular polymer, let me draw it. So for lattice series, we always have very symmetric phase where, let me redraw other half. So it's always going to be very symmetric. So Tc always relate to a phi c. And Tc phi c defines as critical temperature, and phi c defined as the components of one material at this critical temperature. In other words, if it's symmetric, then phi c always happens at 0.5. But if you have a polymer in solvents, your phase diagram typically is not symmetrical. It's going to be skewed over one direction, then your phi c is not going to be as symmetric as you would expect. It's not going to be 0.5, and this can be also determined based on what our understanding of Flory-Hagen theory. And this is where we're going to also talk briefly what is phi c value is. So let's go back. So phi c value is basically can be defined using equation above, where our first derivative of the Flory-Hagen's parameter can be defined as equal to 0. Using that relationship, we can basically back calculate out what it would be the phi c at this critical data points. So the equation is quite simple. What you need to do is to rearrange it and apply where n1, n2 is, and this would be the conclusion. And if you think about what I just mentioned in the lattice theory, if you think about lattice theory, that phi c is 0.5, right? It's usually symmetric, and when the critical temperature, your phi c is 50-50 mixture at the middle of the curve. You can apply n1, n2 equals to 1, which is the case of lattice theory. Then you can see root square of 1 is 1, and in the bottom you have 1 plus 1 equals 2. So phi c is 0.5. And how about for polymer in solvents? Then phi c would be example of root 1, which equals to 1, and root n1 equals to 1 will be equals to 1 again, but you have a root n. So if degree of permutation is, let's say, 100, not particularly high, right? dp of 100, then you can get phi c. Phi c is right about 1 divided by 11. So that's about 10%. So we go back. That means this is no longer 0.5, and phi c will just be 10, about 0.09. This is 1 divided by 11 roughly, and this is at the degree of permutation equals to n equals to 100. So you can see the phase curve will not be symmetric. It will be skewed towards leftward, okay? Again, there is some additional, if we substitute the above relationship, we can also get a definition of where chi critical depends on the molecular weight. And this is simply by plugging in what is phi c is. And this critical c, what would be the chi critical is given by this particular equation as well. And if you know the chi c, you can also simply go back to the relationship one more time to apply into this Ts, and you get critical temperature Tc. Okay? So that defines what is 3 critical parameter in the phase diagram. At the tip of it, what is a Tc value, what is phi c value, and what is chi c value in the phase diagram. Okay? So this pretty much summarized most of what we need to discuss about phase diagram, and I think we already discussed how we can achieve different data points. And this is another recap of what we discussed. So binodal curve will need to be defined by a tangent of a linear line with respect to your delta G curve or free energy curve. So this is defined by this red line where it intercepts. So you would get the data point A and E. Spinodal curve will be defined by second derivative of the delta G equals to 0. And this defines this data point B and D. This is when your curve starts to transit from the concave up to concave down, and B is where the transition point. And you would also have critical data points where is there. This is a critical point. At this point, you have spinodal and binodal curve meet, and you would have a special relationship where first, the second, and third derivative of delta G would always be 0 at this unique data point. And at this critical point, we can calculate out what is phi c, critical concentration, or concentration at this critical point. Okay, and here is an example where, again, I want to show the molecular weight dependence. If you increase the molecular weight, this is what happens in one of the reported results, where your critical data point is shown here, where at higher molecular weight, your phase diagram is more skewed towards one direction, and this is due to the Flory-Huggins parameter problem. We talked about the entropy contribution for the polymer is reduced due to the linkage of the polymer, and that's without this increase. Shifting of the curve all on the left, as you see, the plot is only between 0 to 0.35 in the bottom of the axis. Okay, there's a large part having to show. And second is your Tc is also going to be dependent on the temperature, as we define here. You would also need to be able to use that to understand what the phase behavior of a particular polymer in solvent. Okay. We're only going to talk briefly there. This is not covered in the textbook, where the polydispersity also have influence in the mixing of the material. And polydispersity influence can be also captured by the Flory-Huggins parameter. And we can use, again, the classic Flory-Huggins equation, but it was consideration of what is a phi 2 or what is the dispersed phase. And this results in a broadened transition in terms of phase behavior. And this is what we show here in the bottom. What the phase behavior now used to be a very sharp curve. Now it's become broadened, and as shown is the example here. It will not change dramatically your phase behavior, but certainly will make the phase behavior a little bit tricky to study. Last, there's 2 points we want to make about the limitation of the Flory-Huggins theory. There's a limitation when people develop this theory. It is more or less a mean field theory. That means it does not consider individual or local property, but only consider the property as a whole and take average out of it. So Flory-Huggins theory does have a few limitations. And we're only going to discuss one major one, and that is the theory works better for more concentrated solvent or in the binary of the blend in the melt. What this means is when you have two binary blends in the melt, your material system is more satisfied this mean field theory. If it's in the very dilute case, that as you can see here, in the local region, there's area you can find a polymer chain. Then this is a high concentration region, and this is a low concentration region. And high concentration region certainly will be much higher than system average. What system average means is where you take the number of the chain divided by total number of square. Or if we speak the language of the polystyrene again and dissolved in hexane, then polystyrene, if it's only 1 mg per mil or 0.1 mg per mil, then you would potentially have a problem that if you have a magnifying glass and you find in the solution where you can catch a chain in the region of interest, then your concentration is definitely going to be higher because a single chain in that local volume is bigger than average. Okay, this is a problem because mean field theory does not take consideration into local fluctuation into effect. It's pretty much like put a black cloth in this particular checkbox and assume everything is average. And this is pretty much the case when you have concentrated solution. Example is shown here where now you can see this assumption holds better, where you look around different regions of the checkbox and the average concentration of what you find is going to be more closer to average solution concentration. So this holds even better in the concentrated case where you just have the binary melt. Okay, so that's pretty much summarized what I want to talk about. So I'll leave about 10 minutes for the question related to the Flory-Hagen theory and the phase behavior of the mold material. And starting next lecture, I'm going to have some extra work to talk about. So next Tuesday, we're going to have a lecture about concentrated region. This is not discussed in the textbook, so you are not necessarily able to find in the polymer chemistry book, but it's pretty much covered in other textbook. Talks about what if you have the solution is more concentrated. Okay, so it sits in between the very dilute case versus the melt case, and we're going to spend a lecture or two to discuss with it. I'm going to then go back to the Zoom and see if anyone have any questions. Okay, so please ask me questions if you have related to today's lecture. I will be here. If you don't, feel free to go, and we will get back to the class again in about a couple days in next Tuesday. Okay?
Dr. Q, I have a question.
Yeah, please.
So for the equation chi goes to A plus B by T, what is that A and B talking about the zero coefficient that we talked about before? Is it the same thing or is this something new? You mentioned it's constant, and then when I look at the book, it doesn't say what it is, but it only talks about what is it telling if it's negative or positive.
Kundu, you are right about that. First, let's clarify one thing. A and B are constant, and they are not necessarily widely reported, and you can find them in many textbooks. So a lot of time in the textbook, because it's very material system specific and very combination specific, you should be able to find in published literature where, for example, toluene and polystyrene will give you a combination of A and B. And these going to be a constant specific to this material system. And in the textbook, they probably discussed what if the sign of A and B would impact your LCST and UCST behavior, right? So let's discuss briefly, use this opportunity to talk about that. So in general, chi can be discussed as this particular equation as you see on the board. And now there's two cases where we talk about. There's a UCST behavior where your polymer would behave.
Sorry to interrupt. Are you turning on the video?
Yeah, if you're drawing, we can't see it. I think you don't have it turned on.
Okay.
Would you guys be able to see on the YouTube? I don't think I turned that off, but there is a little bit delay. Yeah,
it's on YouTube.
Yeah, I'll mute my Zoom. Then let's focus on the YouTube. Then I'll come back again. Okay, because that way. Okay, so coming back to the topic about UCST and LCST and how it depends on the A and B constant value, okay? So as you can see, UCST is what it means is upper critical point. So this is where the T critical point. And this means that this will be two phase at the bottom of the phase diagram, and this will be the one phase, right? And what this particular example tells you is that when I increase the temperature, my polymer tend to dissolve better, okay? So if we look at a temperature profile from the bottom to top, I could go from a two-phase and with increase the temperature, and now I would evolve into one phase from here to top, right? This means your system is start to be more likely to mix. And this happens another way you can think about the problem is your chi for the system goes down with respect to temperature. So that happens, depends on the chi value. As we know that chi, if it's much bigger than 0, the system will not easy to mix. So that means it doesn't depend much on the A constant, but it depends on the B. So if B is larger than 0, as you can see, when the temperature goes up, B divided P will go down. And this means overall chi will reduce. So this means your system will likely to behave like UCST. On the other hand, if you have B is negative, if temperature goes up, B divided by T will go up. Why? Because B is negative. Okay, negative 10 divided by, let's say, 200 and 100, you will get, when temperature goes up, your value is closer to 0, so it will go up. What this means, chi will increase in this case, generally speaking, and your system will more likely to phase separate. And this would translate into a UCST, LCST, sorry, misspelling. Lower critical temperature, so which shows here. You have a critical point at the bottom, and you have one phase in the bottom and two phase in the upper. That means when I increase the temperature, my system will go from well dissolved one phase, and if I keep heating up, and your chi is start to increase with the temperature and will eventually phase separate. Okay? But those are just more like a generic term. Absolute value with comparison between the chi and entropy will be more precise because it's only qualitative discussion here. All right, now I'm gonna stop here and go back to Zoom. Okay, so any more questions? Did this answer your confusions?
Yeah, that was good. Thank you.
You're welcome. Okay, any other question? If not, then I will end the live cast on Zoom and YouTube and then see everybody next week. Okay, then enjoy the weekend, everybody. I'll talk to you guys next week.
Bye.
Okay, bye-bye.